Most of us are able to intuit mechanical heating, spark, fuel, air. Not so much with cooling. There are two non-obvious rules of physics needed to visualize the compression refrigeration cycle, the air conditioning cycle. The first rule is that the heat of vaporization is powerful. It just takes a lot of heat to change a liquid into a gas. In this process of changing a liquid to a gas, we will call interchangeably evaporation or boiling, depending on which word seems more intuitive for the process that we're trying to describe. But for our purposes here, we can think of them as the same thing. Now, the reverse of that holds also. We require heat to change to a gas, but we produce heat when changing a gas to a liquid, and we'll call this condensation. So coolant that is evaporating or boiling is cold, and coolant that is condensing is warm. That's important. The second rule of physics we need to buy into before proceeding is as follows. The boiling point of a fluid is a function of pressure. You already knew it was a function of temperature, but it's also a function of pressure. Low pressure induces boiling. You may think of low pressure as kind of pulling apart the denser liquid molecules and thus changing their state to a gas. High pressure induces condensation. Again, we can think of high pressure compressing the dispersed gas molecules into a denser liquid. And all this boiling and condensing can be accomplished by pressurizing and depressurizing the coolant. You've likely heard that water boils in the high altitude environment, which is another way of saying low air pressure environment of Denver, at some lower temperature. Well, it does. It boils there at about 195 degrees Fahrenheit rather than 212. And the opposite holds. Instead of 212, water boils in a pressure cooker at about 230 degrees Fahrenheit. This is important stuff because it means that if we put coolant in a loop, boiling can be induced by reducing the coolant's pressure in the evaporator, and this makes the evaporator cold. And condensation can be induced by simply increasing the coolant's pressure in the condenser, making it warm. And so it goes, round and round, low pressure to high pressure and back, evaporation to condensation and back. You directly experience something like mechanical cooling when operating in an aerosol can that, when sprayed, has cooled in your hands. What's happening there is this. By releasing the nozzle, you release some of the pressure inside the can. And we already found that with decreasing pressure comes boiling. The fluid is turning to gas. Boiling requires heat in order to change the liquid into a gas. And your hand feels colder because that can sucks the heat away from your hand to facilitate a state change inside the can itself. The can feels cold. The compression refrigeration process. Let's diagram the compression refrigeration loop. Air conditioning. We'll start with a looped tube, a closed looped tube, and we'll fill it with coolant. Coolant or refrigerant is a fluid that, in this case, has a boiling point somewhere near room temperature. A fluid may be a liquid or a gas, and here, it will be a bit of both. Now, let's insert a pump into our closed loop of coolant and begin circulating the coolant around. At the other side of our diagram, opposite the pump, we'll insert a valve. Think of a faucet that's almost closed, letting just a bit of fluid through, but keeping most of it back, building up pressure on the upstream side of the valve. Very quickly, we'll see that we have most of the fluid on one side of the loop, a high-pressure side downstream of the pump and upstream of the valve. The other, low-pressure side, downstream of the valve and upstream of the pump, has less fluid because the pump is busy trying to move the fluid around faster than the valve is letting it through. Here we draw from our aerosol can example. On the high-pressure side, we are pushing, squeezing the gas molecules, forcing them into a liquid state. And on the low-pressure side, we are ripping the molecules out of their liquid state and into a gaseous state. We are condensing on the high-pressure side and evaporating or boiling on the low-pressure side. Remember the power of the heat of vaporization? Boiling requires heat. It makes things cold. and condensation gives heat. It makes things warm. So by boiling on one side and condensing on the other, we are creating a cold side and a warm side of our pipe. Now, let's position the cold side on the inside of our building and the warm side on the outside of our building, and add 2 fans, one per side, to bring air over each pipe. We might then draw in room air at room temperature, say 70 degrees Fahrenheit, run it over a cold pipe, and supply it back to the room at 50 degrees. Likewise, on the outside hot loop, the one with the condensing coolant, we will utilize a fan to draw 80-degree outside air across the hot pipe and deposit it back to the outside air at 90 degrees. We now ensure that the 2 air streams don't come into contact with one another. We'll put a little wall between them, and you'll recognize that we've diagrammed a window air conditioning unit. In technical parlance, this type of equipment is also called a unitary system or a direct expansion system, and direct expansion is sometimes abbreviated to simply a DX system. This is a window unit, the simplest manifestation of air conditioning we see in buildings. But even the more complex versions of this system, the ones we'll see in forthcoming diagram animations, will essentially entail the same process, only heat will move around in a more efficient way, or will be used to service more than just one room, or both. Compression refrigeration components. Picking up where we left off with our compression refrigeration loop, remember we have a condensing side under high pressure, where gaseous coolant transitions to liquid coolant. It's the hot side, and over opposite it we have an evaporating side, under low pressure, where liquid coolant transitions back to gas. It's the cold side. Each side has air blowing across the pipe. Importantly, it's not the coolant itself that comes into direct contact with the air, but rather it is the pipe that carries the coolant that exchanges heat with the air. Now, since the air blows across the pipe for the purpose of moving heat, efficiency dictates that we would prefer to maximize the surface area of each pipe to facilitate heat exchange. We will draw it like this, as a squiggle, and refer to each heat exchange squiggle as a coil, though it may, in practice, look more like a series of metal fins. The part of the loop where evaporation takes place, the cold side, is termed the evaporator, and the portion of the loop where the gaseous fluid condenses is termed the condenser. What we were calling the pump that moves the fluid around is actually termed the compressor, and the valve that lets only a bit of fluid through at a time is called the expansion valve.